In this presentation, we will cover our fourth circuit theorem, which is the Norton's theorem. Norton's theorem is very similar to the Thevenin's theorem. Norton theorem states that a circuit A can be replaced by a parallel resistance and current source. Replacing the circuit A with the Norton equivalent circuit does not change the voltage and current of any elements in the circuit B. Actually, Norton's equivalent circuit is simply the source transformation of the Thevenin equivalent circuit, and therefore, in order to find the Norton equivalent circuit, we need to do the same operations which we did for the Thevenin equivalent circuits. These are finding two of the following: open circuit voltage of circuit A, short circuit current of circuit A, or Thevenin resistance of the circuit A star, which is the version of the A with the short-circuited voltage sources and open-circuited current sources. Let's find the Norton equivalent circuit. What would be the easiest thing to do? I can find the plus minus V open circuit voltage here. I have here a simple circuit consisting of a voltage source and 3 series resistors. Therefore, I will use the voltage divider rule. V open circuit will be equal to 6 kilo ohms divided by 8 kilo ohms plus 6 kilo ohms plus 4 kilo ohms times the 15 volt supply voltage. According to this will be 1, this will be 3, and this will be 5 volts. I found the V open circuit as 5 volts. Secondly, let us try to find the R Thevenin by short-circuiting the voltage source. I short-circuited. Here I have 8 kilo ohms. Here I have 4 kilo ohms. Here I have 6 kilo ohms. And I need to find the equivalent R Thevenin from these ports A and B. So here I have node A, here I have node B. And 8 and 4 are in series to each other. Resultingly, I actually have here a 12 kilo ohms equivalent resistor. And this 12 kilo ohms is in parallel with 6 kilo ohms. Therefore, RT is equal to 6 kilo ohms in parallel with 12 kilo ohms. And this is equal to 1 over 6k plus 1 over 12k. And accordingly, 4 kilo ohms. So I actually finished the solution of this circuit because I can calculate I short circuit simply as I short circuit V open circuit over R Thevenin, and this will be 5 volts divided by 4 kilo ohms, and if I am not wrong, 1.25 milliamperes. So according to this, the Thevenin equivalent circuit will be 1.25 milliamperes here with a parallel, not series, resistor of 4 kilo ohms value. And here I have the output ports A and B. But in addition to these, I can also solve this circuit by finding the I short circuit. How will I do that? Let's draw. Let me use a different color. Plus minus 15. Here I have 8 kilo ohms. Here I will have 6 kilo ohms. And in parallel to that, I will have the part where I have I short circuit. Now, please be careful. Actually, with the I short circuit, I am bypassing the 6 kilo ohm resistor because no current will flow over 6 kilo ohms if they can go simply through the I short circuit. Accordingly, I short circuit will be equal to 15 volts divided by 8 kilo ohms plus 4 kilo ohms, and this is also equal to 15 over 12, which is 1.25 milliamperes. So I basically verified the solution which I found in the upper part by finding the I short circuit with an alternative way. Alright, let us try to solve this question. I want to first find I short circuit. What will be I short circuit? Assuming that this is the reference node, when I short circuit this circuit, I will have 0 here and 0 here. So in other words, VAB will be equal to 0. If VAB will be equal to 0, I basically will have no voltage source here. The circuit simplifies quite a bit. Let me redraw my circuit then. Plus minus 5 volts. Here I have 500 ohms. Here I have I. Then I have here 10I. And no current will ever pass over this 25 ohm resistor because all of that will flow through the short-circuited A and B nodes. So I short circuit is flowing this way. Now this left side of the circuit is independent of the right side. So I have 5 volts and 500 ohms. Simply I will be equal to 5 volts over 500 ohms, and this will be equal to 10 milliamperes. If I is equal to 10 milliamperes, here I will have 100 milliamperes flowing, and 100 milliamperes will be equal to minus I short circuit. Accordingly, I short circuit will be equal to 0.5 minus 0.5 amperes. So I found the I short circuit. In the previous slide, I have calculated I short circuit, and I found I short circuit as minus 0.5 amperes. Now I want to find V open circuit, and for that I will cut this connection. And V open circuit will be equal to VAB. In other words, I can here remove VAB and write here V open circuit as well. If I assume that this bottom node is the reference node, I will have V open circuit at this point as well. Now, here the current I is flowing over this loop. So let us write the Kirchhoff's voltage law for that loop. 500 times I plus VOC will be equal to 5. And let me also write the Kirchhoff's current law for the VOC here. VOC over 25, the current going out this way, plus 10I will be equal to 0. Let's simplify this a little bit. VOC plus 250. I is equal to 0. Let's write this equation here again. I will change the places of the terms VOC and I plus 500. I is equal to 5. Let's call this equation 2 and let's call this equation 1. I will subtract from equation 1, equation 2, equation 1, and I end up with 250I is equal to 5 volts. From here, I is equal to 20 milliamperes. I found I. Now I need to find VOC. Let's take this equation again. VOC plus 500 times 20 milliamperes, this will be 10 volts, is equal to 5. From here I find VOC as minus 5 volts. If VOC is minus 5 volts and I short circuit is minus 0.1 amps, our Thevenin is equal to minus 5 divided by minus 0.1 volts amperes and is equal to 50 ohms. Accordingly, I can draw the Norton equivalent circuit as 0.1 amperes flowing downward with a parallel resistance of 50 ohms, and here the ports A and B, and this concludes the solution of this example. I need to find the Norton equivalent circuits. I will start doing this by finding the R Thevenin or R Norton by short circuiting the 24 volt current, voltage source and open circuiting the 3 amps current source. Accordingly, the circuit will become simply two resistors and the nodes A and B. 4 ohms and 12 ohms are in parallel. Therefore, our Thevenin, which is equal to 4 ohms in parallel to 12 ohms, and the result will be 3 ohms. Now I need to find the I short circuit. I am connecting these two. I write here I short circuit. Now, as soon as I connect A and B, no current will flow over 12 ohm resistor because I have an alternative path through which there is no resistance. So current this way will be equal to 0. Moreover, here I have the reference node. The reference node is equal to 0. But as you can see, since the reference node is connected to the upper part of the circuit with no resistance, I can write that this part of the circuit is 0 volts as well. Now, the only thing I will do is to write the Kirchhoff's current law for this node. So 0 minus 24 over 4 is the current going this way. We have 3 amperes entering, so I will write that as minus 3 plus the current going out is I short circuit is equal to 0. So here I have minus 6 minus 3 plus I short circuit is equal to 0. And from here I calculate I short circuit is equal to 9 amperes. Since I have I short circuit and I have R Thevenin, I can draw the Norton equivalent circuit as 9 amp current source, and in parallel to that the 3 ohm resistor.